Oh, I've been solving leak code problems since I was a little kid. This is 2087 minimum cost homecoming of a robot in a grid. Let's fix that. Put that over there. Okay. So there's an M by N grid where 0, 0 is the top left cell and M minus 1, N minus 1 is the bottom right cell. All right. Well, we might as well just draw that out, right? Might as well get some information about what this problem really looks like. All right, so we got 0, 0 at the top left corner. And then we have, MN over here. And then some sort of elaborate rectangular grid with dimensions M, N. And I overshot it, right? So here's our little square grid. Not so beautiful, but it is what it is, right? And, there's M rows and N columns. So just to add a little bit more notation so we can kind of understand what's going on here, right? We have M dimension here and we have N dimension here, right? So this is a pretty standard orientation for problems, right? You have a grid, it's got rows, it got columns. You have M rows, you have N columns. So technically, if this position is 0, 0 at the top left, this would technically be position M minus 1, N minus 1, okay? So that's the orientation of this grid. And you're given an array start position where start position equals start row and start column. Okay, so there's some position within this grid where you start, and there's a robot that's in that position. You're also given an integer array home position. Home row, home column indicates that the home is at home. So you have the position of the robot, okay, and that's at the start position. And then you have the position of the home, which is in some other position, right? Maybe like this. Okay, and that's all specified by start position and home position. So the home position is here because it's in home row, home column. The robot's here because it's in start row, start column. Okay, the robot needs to go to its home. It can move one cell in 4 directions. Okay, so the robot has the mobility, right? Mobility is important in these problems because sometimes you don't have full mobility. But it kind of makes sense, right? The robot could go up if he wanted to. He could go left if he wanted to. He could go down if he wanted to, and he can go right if you want to. Right. And this robot would probably, like, depending on how much it costs, right? If we're trying to minimize the cost, whatever we're trying to do, right? He's gonna move here and maybe move here and then move down, something like that. Right. But who knows? But you can kind of see that happening, right? He can go left, he can go down, he can go up. He's got full mobility in all directions, all two-dimensional directions. Okay. And it cannot move outside the boundary, okay? So it can't, like, go this way and then try to jump off the map or something weird like that, right? Okay. Every move incurs some cost. You are further given 2 0-index integer arrays, row cost of length m, and call cost of length n. Oh, I have to sneeze, but I can't. In English, I don't know where you guys are from, but if you say watermelon, in American English at least, apparently that makes you sneeze. Watermelon, 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 watermelon. Didn't work. Okay. Row cost of length m and call cost of length n. So what does that mean? Well, it's saying that, there's cost associated with going into a column and there's cost associated with going into a row. All right. So if I go into, this row, it's going to have a cost associated with it. Right? If I go into this column, there's going to be a cost associated with it, right? So the second this little R guy says, I'm going to move into that column, this R guy decides to go here, that's going to incur some sort of cost associated with this row column thingy-majig. Okay, so if a robot moves up or down into a cell whose row is R, then the move costs row costs. Right, so when you move up into a row, it costs that much, right? If the robot moves left or right into a cell whose column is C, then the move costs call costs. Right? So if I move this guy into this row or into this column, right, left to right, I'm going to incur a cost. If I move him up into this row, I'm going to incur a cost from row cost, right? And those are specified in these row cost, call cost kind of situations here. All right, so let's go through this little example here. I'm actually going to redraw it out, and then we're actually just going to use one example to determine, what the solution to this problem looks like. Okay, so let's erase all this. And this is a 3x4 system, right? So I'm going to draw a 3x4 grid. Okay. All right. So we draw this little 3x4 grid here. And then we have our little robot. He starts in this position here. And I'm going to try my best to draw a little robot here. All right. And then we have the robot's home in this bottom corner. Now, why is that the home and why is that the starting position? So the starting position is 1, 0, right? So row 1, column 0 here. And the home position is 2, 3. So 0, 1, 2, 0, 1, 2, 3 here. All right. Now, the answer is 18. Well, why is it 18? Well, let's go ahead and let's label the costs associated with each column and each row. So you can see the row costs here, 5, 4, and 3, right? So if you travel downwards into this top row, it's going to cost you 5. If you travel into the second row, it's going to cost you 4. If you travel into this bottom row, it's going to cost you 3. And then on the column side, if you travel into the first column, it's going to cost you 8. The second column, 2. Third column, 6. The last column, 7. Okay, so that means whenever I step into this column going right, whenever this guy moves to the right, it's going to cost me 2 points, right? And if you look at this whole score, well, it's going to cost the final path is this, right? The optimal path. So that's going to mean I go down into 3, I go right into 2, I go right into 6, and I go right into 7. So that's 6, 10, 16, 18 equals 18. Right. And that's how you get 18 here, and that's why the answer here is 18. All right. So when you're looking at this problem, this is a perfect example of a problem where you may not want to be impatient with what you consider is the optimal solution. And what I mean by that is when you look at this problem, you think searching, right? So you think, okay, this is going to be a like Dijkstra's algorithm, right? Or some sort of alternative modified breadth first search, or maybe I can use dynamic programming to find the optimal approach, right? You might feel so pressured into thinking, oh, what are all the data structures and algorithms I can apply to this problem? While the actual answer is much simpler and the complexity in terms of space and time is far more efficient. So you don't want to kind of box yourself in here by using, the obvious answer, because there's actually something that you can conclude, right, from the way that this problem is structured, which will lead you to understanding that, it's kind of overkill. It's too much. It's an overfitted solution. It's far too elaborate to do something like Dijkstra's search algorithm, even though that would technically work here. And all I'm saying here is sometimes, in summary, it's best to not jump to conclusions and kind of think about the problem a little bit and what that indicates about your actual solution. Okay. So what is the actual thing you're supposed to notice about this problem? Well, if you had a system, right, I'm going to try to make a general case, and then I'll go back to the example, and maybe it'll make sense there. But if you had a house that was over here, right? Say your house was over here, and your robot was over here. Okay? Now, in between the house and the robot, there's a column with cost X. Okay? All right, because every column has a cost. So if this robot is going to get to this house, right, he's going to have to find a way there, which means he's going to have to go through this column. Okay? And think about that for a moment. If this robot is going to get to its house, it has to go through this column. Right? And it has to go through this column and incur the charge of using that column, right? Because no matter how this robot moves, right? If it goes here, here, if it decides that it's going to go up here, right? Decides it's going to go back down here and then to the left and down and right and down and up and up and down and whatever, it's going to have to eventually go to the right and go through this column. So that means no matter what, I have to incur the cost of this column with the value X, right? Any column that's between me and the house, I'm going to have to go through it in order to get to the house, right? If there was all these columns in between, and maybe I'll just exaggerate this point even more by drawing all the columns in between the values. I'll put this guy a little closer so I don't have to play this game for too long, right? All these columns in between me and the house, no matter what, no matter how I decide to move through this system, I'm gonna have to, I have no option, there's no alternative, I have to move through all these columns, right? So all these columns with their own, associated cost, my final answer will have to have A plus Y plus X plus Z plus B. Why is my face down here again? I don't know why, but it is. That's gonna have to be the case, right? Because no matter how I move this guy, right? No matter how crazy I try to make him move, no matter how elaborate, how tricky, I have to go through here, right? The only way I can get to this house is if I go through A, and I have to go through Y, and I have to go through X, and I have to go through Z, and I have to go through B. Right? No matter how I do it, that has to happen. That's the only way I can get through. It's kind of like a wall I have to surpass, right? Since it's taking the whole column, I have to go through it in order to get to the answer. And you can see that here, right? In order to get to this house, I had to go through 2. I had to go through 6. I had to go through 7, right? Because I had to cross those boundaries. So no matter what I do, I have to go through there. So every column in the way, I have to incur the associated cost, right? So I'd say the observation here is, right, every column between the robot and the house, I have to occur, I guess. I don't know. I have to add the cost, right? And the same argument can be made for the rows, right? No matter how I move this thing, if I thought of this in terms of the rows, right, it's the same exact situation. Right? I have to, no matter what, I have to travel through all of these rows in order to get to the house. Right? So I have to travel through all these columns to get to the house, no matter how I do it, and I have to travel through all these rows to get to the house, right? And the way of which I do it, it doesn't really matter, right? I mean, it does, and that second point will become clear in a second, but like if I go right, then right, then right, then down, it's the same thing, right? I'm gonna end up taking in all of the cost of the rows between me and the house, and all the columns between me and the house. And the way of which I do it doesn't really matter, because I'm going to have to go through all the columns and have to go through all the rows, right? So I have to go through all the rows between me, and I have to go through all the columns between me, right? And the way in which I do it isn't really that sophisticated. It doesn't really indicate that much. I guess the only thing that you'll notice is that going backwards does nothing, right? If I should just go directly towards the house. Even though I can move in the other directions, only thing that's doing is making me incur more cost, right? There's no situation where I'm going to be here, for example, and I'm going to want to go left. What would going left give me, right? Going left would only add another column now that I have to go through, right? Going left is like, oh shit, now I'm in the same situation, except now that I have to go through this column again, right? So I should always just go through these things and go through them once. So really the answer to this problem is, well, it's just the sum of the rows and the columns that are in between me and the solution, right? The rows that are in between me and the house, and the columns that are in between me, the robot, and the house. Nothing else is important. Nothing else matters. Nothing else will indicate anything. So really all I have to do is I have to look at the house, and I have to look at the robot, and then just sum the rows and sum the columns that are in between them, right? So when I'm looking at this answer, right, I say, okay, if my robot is here, right, I need to add up these rows, right, because I'm going to have to move through all of these rows because they're barriers that I have to pass. It doesn't matter when I do it. It doesn't matter if I zigzag through or I go direct, and I have to sum up these columns, right? That's really all this problem is, okay? So when we look at the situation up here, well, what is this answer corresponding to, right? What does it really mean here? Well, I have to sum up these rows. It's really just one row that I'm traveling through, right? So I have to sum up this 3 row because I have to travel through this. I'm going to make this nice. I have to travel through this 3 row, right? I have no option but to do that. Right, because in order to get the row in between me and the house is the row 3. So it doesn't matter if I cross it here or I cross it later. Right? At some point, absolutely certain, I have to cross into that row, no matter how I do this. Right? It doesn't matter when I do it, but I'm going to have to do it in order to get to the house. So there's going to be a cost associated with that. And then it's the value of these columns. Right? So I have this column here I have to cross, and that's going to occur me 2. I have this column I have to cross, and that's going to occur me 6. And I have this column I have to cross, and that's going to occur me 7. Right? And no matter how I do this, right, it's still going to be the situation that I have to take, right? If I go down first, I'm still going to have to occur this 2. If I'm at 2 and for whatever reason I go back up, which I shouldn't do, right, because it's going to make my score worse, right, I'm still going to have to occur this 6. No matter what I do, I have to occur the cost associated with 2, associated with 6, associated with 7. Okay. So let's, now that we have that understood, all we have to do is find a sophisticated way of finding the values in between each, between the robot and the final car we're going to, okay? So here's how we'll do it, right? We just need to find the rows in between us and the destination and the columns in between us and destination and sum them up. So we'll say res equals 0. That'll be what we return at the end, okay? And then we'll just say, well, how do we know the rows between us and the destination? Well, if the home positions row, that's the first thing, is greater than the start positions row. So we're going from home position, which is higher, and we're increasing rows like this case here, right? The start position's 1, the home position's 2, so we're increasing rows. Well, we have to increase, there's going to be a row in between that we have to add. So we're going to say res plus equal. Now we're going to be incurring row costs here. Now what row costs are incurred here? Well, not the row you start on, right? I'm doing plus 1 here because we're not going to sum up, because we're trying to sum here, right? We're not going to count the row that we start at, right? Because we don't care about where we start. We only add where we're going, right? We don't add a 1 to this solution because it's only when you're going down, when you're moving into a cell, do you incur the cost. We're not moving into the starting cell, so that's why we do plus 1. Hopefully that makes sense, right? In the answer before, right, you add up this cell, this row, this column, this column, this column, not the one you start at. So that's why there's a plus 1. And then you want to do, what's the last row you're going to end up doing? Well, that's the cell that you end up at, right? So that's going to be, I did this wrong. This is start position. I'm sorry, guys. So wherever you start, you're not going to add that up, right? You start adding up on the first row that you travel to, all right? And then the ending position is the ending row, so that would be home position. So I get confused because home position sounds like where you're starting, right? I start from home. I don't know why I'm thinking like that. 0, and then again, it's plus 1 because, you know, an array is not, it's exclusive, right? So exclude the last element. So to include the last element, I increase it by 1, right? So that's if home position is greater than start position. Otherwise, well, we're going up, right? So we could do it in reverse. Can you do? I'm just curious. I don't even know if you can do this in Python, but we're going to find out right now. What if I did like 1 to 0? I just don't know if you can do negative. I'm going to lose my face because I don't care. I don't know if you can do negative thingamajigs in here. No, so you can't do negative indices. So we're going to have to do it like this. Start position is not defined. So else, we're going to say we need to go the other direction. Because now, if it's in this case, it means that you're ending higher up, right? So this is the case where the row is below you. But in this case, the row is above you. So you're going to want to add the rows in between the lower thing to the higher thing, since you can't add rows negatively. It doesn't really matter. Just you're going to end up adding home position. So you include home position, but you don't include the starting position, right? You never include the starting position. So it would be like that, right? Because you go from 1 to 1, now 0, 0. So you can kind of see that this is the same number of elements. And if you want to think about this, you know, kind of maybe draw it out, and you'll see like the connection between these things, right? Because you want to add in the home position, right? Because the home position, you do actually have to go into that row. So you're going to incur the cost, right? Which is why you did the +1 here. But you don't want to include the start position because that's where you actually start. So you do it exclusively, and this won't include the start position. And that's why it starts start position +1 here. All right, and then the column is the same exact game. So you just go here, but you're going to do the same thing. You're just going to change. You know, now we're looking at the column between home position, start position. It's call cost now. And this is why it's sometimes good to really understand the logic of these things, because you can easily, you know, get through your associated code here. 1, 1, everything should be 1. All right, good enough for me. I am ready to try. It's weird I can't see the... All right, run code. Submit. All right. So what is the runtime and complexity of this solution? Well, it just so happens. No. Well, it's pretty simple, right? So let's just do n equals the length of... So we have an n by m grid, right? So let's say m is the length of row costs, and n is the length of call costs. All right. Well, for time, let's do space first, because space is a little easier here. All we do is we create one variable. That's it. We create one variable, and then we add to it. Right? We don't create any other temporary variables, nothing. So that's O of 1, constant space. For time, a little bit more complicated, because well, we have to sum all the rows in between the start position and the home position. It's possible that I'm at row 0 and the house is at the last row. So I'm going to have to sum values for every single row, and there's m rows. So I definitely have O of m time plus what? Well, we do the same thing for columns, right? If you're on column 0 and it's on the last column, you're going to have to sum values for all the columns. So that's m plus n time, right? You just have to look at the number of rows at the worst case to find out the sum of the rows in between you and the final answer, and the number of columns for the same reason. Okay. All right, guys. Hope you have a beautiful day. Peace out.